we're going to talk about the cross product of two vectors. It's important to remember that this definition only works for vectors in three-dimensional space. This definition only applies to vectors with three components. So I'll start off by defining two vectors, v and w, and I'll name the components of the vector after the vector itself. And now I need to define the cross product v cross w. It's actually a long definition, and so we remember the definition by using some matrix notation. Matrices you'll see a lot of in algebra and linear algebra, and we're going to use a computation that you'll see all the time with matrices called matrix determinant to help us calculate the cross product. Now it turns out when you define a matrix determinant, you'll define the determinant of a 3 by 3 matrix in terms of the determinant of a 2 by 2 matrix, which is calculated. I use this mnemonic for a 2 by 2 matrix, A times D minus B times C. Alright, so I'm going to take this 3 by 3 determinant, and a 3 by 3 determinant breaks up into a combination of three 2 by 2 determinants. Notice I'm going to have a determinant times I, 1 times j, and 1 times k. To figure out the coefficient of I, ignore everything in the same column and row as I, and put the remaining numbers in that 2 by 2 matrix. So in front of I, we'll have the numbers v2, v3, w2, and w3. In the matrix next to j, cross out everything in the same row and column, the remaining numbers go in that position. So the matrix associated to j will contain v1, v3, w1, and w3. In front of k, ignore the row and column containing k. The numbers in that matrix will be v1, v2, w1, and w2. And now each of these 2 by 2 matrix determinants can be calculated with that formula on the center right. Let's do them one at a time. Remember, the determinant in front of j, there's a negative sign there. That'll be important for some of the properties we'll see momentarily. So this, the result, is a vector. It's written in terms of i's, j's, and k's, but remember, those are just the unit vectors in three-dimensional space. If you prefer, you can also write this just in terms of components, using angle bracket notation. And one other important thing to notice as we're doing these calculations, the result of the cross product is a vector compared to the result of the dot product, which is a scalar. Another important thing to note, the dot product is commutative, but the cross product is not. Because it involves subtraction, you'll get something different if you reverse the order. So be very careful about that. Okay, the cross product is a very complicated definition. So hopefully it'll prove its worth by having some interesting properties. So let's circle that. We're going to use it a lot later. Now let's talk about some properties of the cross product. Combining two vectors to get another vector, what's special about that vector we get? I'm going to define a vector n to be v cross w, because I don't want to have to keep on writing v cross w repeatedly. Now what happens when we take the dot product of v with n? There's a whole lot of algebra. I have to do component-wise multiplication. So there's the first components, plus the product of the second components. It's another 2 terms. Plus the product of the third components. So there's another 2 terms. It's an enormous algebraic expression with 6 terms. But if you look closely, something great is going to happen. This first term, it turns out, cancels with the fourth term. The second term cancels out with the fifth term. And as you might suspect, the remaining 2 terms, the third term and the sixth term, also cancel out. That leaves us with v dot n is equal to 0. So if the cosine of the angle between them is 0, the angle between them is a right angle, so the vectors v and n are perpendicular. Now, if you really like algebra, you can carry out this calculation again for the vector w. It turns out to give you the same result. The dot product of w and n is 0, so w is perpendicular to n. We can even take it one step further. What if we have a combination, a linear combination of the vector v and the vector w? And I take the dot product of that with n. Well, thanks to properties of the dot product, I could rewrite this, distributing through vector n, a times v dot n plus b times w dot n. Well, I've already calculated those dot products, they're both 0. So in the end I get 0. So in other words, this combination, any combination of v and w, will give you another vector which is perpendicular to n. Now what does this mean graphically speaking? Well, if I take any linear combination of the vector v and the vector w, the set of all linear combinations actually forms a plane. So I'm going to sketch out the plane containing v and w. Now the vector n, this cross product, is perpendicular to v, w, and everything in that plane. So that vector, you can think of it as being perpendicular to the entire plane. There's v cross w. The reason I use the letter n, we often say that when we're comparing a plane to a vector, we say that the vector n is normal to the plane spanned by v and w, meaning it's perpendicular to everything in that plane. And it turns out this vector will enable us to calculate a number of important things later on. Now, what other properties does the cross product have? There's more than just one. Another property it has, which is similar to a property of the dot product, we could use the cross product to tell us something about the angle between the two vectors. So if I have my two vectors v and w, and I have the angle between them, well, from the dot product, I know how to calculate the cosine of that angle. The cosine of theta is equal to v dot w over the length of v times the length of w. Now, as it turns out, the cross product will give us some information about the sine. And the formula looks very similar to the cosine formula. It's equal to a fraction. The denominator is the product of the lengths. You might be tempted to say, well, the numerator must just be the cross product. But remember, we want a number. It's actually the length of the cross product. Now, how would you check that this is true? It's really just another algebraic process. What I'm going to do is take that formula for sine theta, multiply both sides by length of v times length of w, and then I'm going to simplify it, and hopefully I will get the length of v cross w. So first, I'm going to take that expression with a sign. Since sine squared plus cosine squared equals 1, I can replace sine squared with that radical expression. The reason I would do that is because I know something about the cosine of theta. Specifically, I have that formula for cosine of theta. And I'll insert it right there. v dot w over length of v times length of w. Remember, that whole quantity is being squared. Next, I'm going to take the lengths of these vectors and move it inside the radical. It becomes squared as we move it inside, and I have to distribute it to each term. So now I have the length of v squared times the length of w squared in place of the 1 minus, well, the length of v length of w squared cancels out the denominator of the pre-existing fraction in the radical. And then you can do a lot of algebraic simplification. You can actually write using the components of the vectors. What is the length of vector v squared? What is the length of vector w squared? Minus the length of the dot product squared. So you take that expression, you simplify it as much as you can. Now remember, our goal is to show that this expression is equal to the length of v cross w. So you keep on doing a lot of algebra. You can check for yourself, but you can actually keep simplifying it and rewriting it and regrouping terms until you get, until you get the length of v cross w. It's a lot of messy algebra, but it works out. So you have a different way to take a look at the angle between two vectors. It's always good to have multiple ways to calculate the same quantity. If you wanted to determine the angle, you could do the arc sine of vector v cross vector w. Now, one final useful property about the cross product is it'll give you information about the areas of parallelograms spanned by two vectors and the volume of a three-dimensional parallelogram or parallelepiped. Let's say I have two vectors, v and w, and you might remember when we talked about vector addition that v and w, 0, and v plus w form the vertices of a parallelogram. What if you wanted to calculate the area of that parallelogram? Well, the area of a parallelogram is base times height. The base is the length of v. What's the height of that parallelogram? Well, you can use the properties of trigonometry. I know the angle between v and w. The length, the height, is the length of v times the length of w. The length of this side is the length of w. The length of the base is the length of the vector v. So to calculate the area of any parallelogram, I need base times height. I can calculate base, and I can calculate height. This expression might look familiar. We actually just talked about it. It's actually the length of the cross product of v and w. So you can use the cross product to calculate areas. Now, there's a three-dimensional analog too. If you have two vectors, v and w, and then a third vector, I'll call that vector u. V and w form a parallelogram in the plane, but then with a vector u, if I connected them, it's not a rectangular prism, because they might not be at right angles. It's like an analog of a parallelogram. The three-dimensional version is called a parallelepiped. Opposite sides are parallel, and each side of this figure is a parallelogram. Now, to calculate the volume of a parallelepiped, I need the area of the base times the height. Now, the area of this base, well, we just calculated that. It's the length of the cross product of v and w. Now I just need the height. Problem is I can't just use length of u because u could be at a slant. What I can do is, if you recall, one of the great properties about a cross product is that it's perpendicular to the plane. So in other words, I can use that as an axis against which to get my height. I need to take the vector u, and I actually need to project it onto v cross w. And when we talked about dot products, we talked about how to calculate the projection of one vector onto another. So I'm going to put this all together. The area of the base I've got times the height. So I don't actually need the vector projection of u onto v cross w. I just need the length. So I'll just use the first part of the projection formula, which gives me the length. I don't need to include the unit vector part. Right. The volume is these two things multiplied together. And you might notice there's great cancellation. All you're really left with to calculate the volume of the parallelepiped is this expression, also known as the scalar triple product.